We'll start. So thank you everybody for being back. We had a great talk this morning covering all theoretical aspects of quantum networks. So for this talk, we have the great pleasure of having today here with us Professor Nathalie de Leon from the Department of Electrical and Computer Engineering at Princeton University. So Nathalie received her Bachelor of Science degree in chemistry in 2004 from Stanford University and her PhD in chemical physics from Harvard in 2011. After that, she worked as a postdoctoral fellow supervised by Miha Lukin and Hongo Park. And her thesis is one of these spectacular results in many things that she might be showing later today. And because of that great work since 2016, she's been a group leader at Princeton, and her research efforts focus on building quantum devices using color centers to realize quantum networks and nanoscale sensors. One great aspect of her research is that it's very interdisciplinary and includes studies in a variety of topics, including nanophotonics, device physics, quantum optics, spectroscopy, and material science. So there's all these great things all combined to form quantum networks, and we are really looking forward to hearing more about that. So Nathalie, the floor is yours. Thank you so much for being here today.
Thank you so much for the kind introduction. It was very, very kind, and thank you for the invitation to come speak at the International Quantum Summer Summit. So let me just say, I know it's always a little bit awkward to interrupt with questions over Zoom, but I'm happy to take questions if people want to sort of chime in the middle of the talk. It's a little more fun to be interactive rather than yelling into the void. So I'll be talking about the work that my group has been doing over the last few years on trying to find new quantum defects in the solid state, specifically for the purpose of building up quantum networks. So just a short, broader introduction to my group. In general, we're interested in atom-like systems in the solid state. Over the last few decades, there has been this really amazing set of experiments on developing atoms as a platform for doing quantum information science. And there have been two main properties that really enable a lot of this science. The first is that you can have these very long-lived quantum degrees of freedom, usually in, for example, the electron spin of a particular atom. And you can basically use that as your qubit states. And then the second is that you can manipulate and measure these qubit states using very efficient optical transitions. So just by sort of shining in lasers, you can both initialize and prepare and then measure the states of your atom. So there have been, many experiments over the last few decades in building up quantum systems based on cold atoms that are cooled in ultra high vacuum with lasers. And one vision is to try to find systems that look a lot like this without all of the overhead associated with things like laser cooling. So what we're really interested in doing is finding systems that essentially act like atoms but exist in the solid state. Both to decrease your experimental complexity, but also because there's now this vision that you could, once you're in the solid state, actually integrate these quantum bits into scalable devices. So for example, you could imagine using a lot of the technology that we have for micro and nano fabrication to build up photonic integrated chips, and other large scale devices. So these atom-like systems in the solid state have a lot of different application sets that are sort of broadly in the category of quantum technology. So of course, they have a lot of implications for quantum information processing, like quantum computing and quantum simulation. Because you can have these optical degrees of freedom and connecting your spin states to things like photons, you can also imagine building up long-distance quantum networks based on these atom-like systems. And then another kind of interesting opportunity, because these things exist in solids, is to use them as nanoscale sensors. So because they're really confined to these atomic dimensions, you can bring them very close to other things and then take advantage of the very high sensitivity and resolution that you can achieve in such systems. Okay, so the topic today is mostly zooming in on quantum networks. So there's a number of reasons why you would want to build a quantum network. So the first, sort of the original sets of proposals around quantum networks all sort of dealt with quantum communication. So the general idea is that if you can communicate over very long distances using quantum states, then there are a number of protocols where you can, for example, guarantee the security of your communication channel using the laws of physics, rather than unproven statements about computational complexity. So, currently we sort of encrypt information and then rely on the fact that it is computationally too difficult for anybody with a current computer to be able to decrypt our messages. And quantum communication sort of offers a completely new solution where the security is really just guaranteed by physics. So it doesn't matter what kind of computer somebody has developed or has access to. There have also been a number of proposals over the last decade on trying to build up quantum networks of small quantum computing. So basically, these are modular quantum computing schemes where you have small processors and then you link them together with some sort of flying qubit, usually photons. This has been proposed, for example, as a way to scale up trapped ion quantum computers. And then finally, there are a number of more recent and exciting proposals about building up quantum networks for very long baseline quantum metrology. For example, in this proposal from several years ago, where they considered what you could do with an entangled network of atomic clocks. So it's sort of worth just, taking one step back and discussing, what we mean by a long distance quantum network in the context of classical communication. So, classically, if I wanted to send light over if I wanted to send a signal over a long distance, then I'm going to use photons. And in general, if I send these photons through, let's say, an undersea cable, then you'll eventually run into just exponential attenuation, because anything is going to give you exponential attenuation. That's just Beer's law. And in order to sort of boost the signal, what people do is they build these repeater stations every n kilometers, so that the signal can get all the way over to the other end of the ocean. So quantum mechanically, we don't have an easy way to build these repeater stations because in quantum mechanics, measurements are inherently perturbative, so they're going to sort of screw up the states that we're trying to send. And there's something called the no cloning theorem that says that you can't arbitrarily copy a quantum state. So there's no way to sort of intercept the state, regenerate it, and then send it on its way. So you need something that's sort of fundamentally different in order to extend the range of quantum communication. So there have been a number of schemes proposed over the last, I guess, 2.5 decades now, for how you could extend the range of quantum communication that all sort of go under this general title of quantum repeater schemes. So the general idea is that if I'm trying to get from Alice to Bob over a very long distance, like say hundreds of kilometers or even thousands of kilometers, what I can do is break up this total distance into much shorter segments, where these short segments are short enough that my attenuation of a single photon is not prohibitively large. And then across each of these short segments, what I can do is place two memories that I can use, that have some sort of long-lived quantum degree of freedom. So these are quantum memories. And then if you entangle these quantum memories with a photon, and then send these photons to a beam splitter that's positioned halfway between these, then thanks to the magic of two-photon interference, these photons are going to bunch into one detector or the other. They won't probabilistically split into both. This bunching erases the which path information between your two memories, and that creates a remote entanglement. And then I can basically do very similar operations to swap entanglement. So I now have, say this segment of an entangled pair, this segment of an entangled pair, this segment. And then I can do this operation again to swap the entanglement, so that now I have these two memories that are farther apart entangled, and then continue to propagate this along the chain until I create an entanglement between the two ends. Now, from what I've drawn here, or from what I've stolen from the internet here, it's not obvious that you should win with these kinds of schemes, but it turns out that there's a very simple mathematical argument that instead of having exponential scaling with distance, you now have polynomial scaling. So these are currently sort of the only way that is known to get to these sort of 1,000-kilometer length scales for quantum communication. So these schemes have been around for a very long time, but the number of even just lab scale demonstrations is pretty few and far between. And the reason is that the physical requirements are actually quite difficult to achieve. So, the first requirement is that you need something that acts as long-lived quantum memory. And specifically, it has to live long enough that you do all of this, these sort of entanglement swapping operations, and you still have meaningful coherence at the end of all of that. The second is that you need to be able to connect this memory to your photons. So, usually you need to find something that acts as a very efficient spin photon interface. And then in order to do this, this two photon interference operation that I discussed earlier, the photons really have to be perfectly identical, which means that they have to have the same spatial mode, same polarization, same wavelength. And that turns out to be actually quite difficult to achieve for a number of systems, because you can either have spectral inhomogeneity where things are off resonance with each other, or even worse, you can have dynamic inhomogeneity where their color, the wavelength of your light is changing over time because of fluctuations in the environment. And then finally, if you really wanted to take advantage of the long propagation lengths that you can get at optical fiber, and not have to build, say, a network of satellites, what you would really want is for these photons to be at telecom wavelengths, so out at 1.5 microns to achieve very long propagation lengths. So the approach that my group has been working on is trying to find candidates for these single atom quantum memories by looking at color centers in diamond. It turns out that if you just pull a diamond out of the ground, any diamond, even if it looks optically transparent to the eye, there are a number of defects in the diamond, crystallographic defects and heteroatom contaminants that give rise to a lot of colors when you shine UV light on it. So these are, it's always funny to show these pictures because we obviously don't really look at gemstones in my group, but if you take gemstones and you do UV photoluminescence, you see lots and lots of colors that pop out. So diamond is a very nice host material for these quantum applications, both because you have the potential to host all of these different defects because you have this very large optical transparency window, and also because the dominant isotope of carbon is carbon-12, which you can also isotopically purify to get mostly carbon-12. And that means that you have the potential for a very low magnetic noise environment, which will give you very long spin coherence times. So our approach is to look for color centers that have all of the essential characteristics that you would need for a single atom quantum memory. So we want something that has a very long electron spin coherence time. We want these photons to be well behaved. And one sort of parameterization of that is that we want photons that exhibit very low spectral diffusion, which just means that the color is stable over time. One way to physically guarantee that is to look for color centers that have a very small permanent dipole moment, because then they will not couple to fluctuating electrostatic fields as much. And then for a variety of reasons having to do with the phonon band structure of diamond, it's actually unlikely that we find really high quantum efficiency defects out in the telecom band directly, but we can kind of do the next best thing and look for near infrared optical transitions where people have already demonstrated efficient wavelength conversion from this band out to the telecom. So most of the work in this field has focused on a single color center diamond, the nitrogen vacancy center. You basically take 2 carbons out of the diamond lattice and put 1 nitrogen in. So you have a nitrogen that's sitting in a substitutional position next to a vacancy in the lattice. This defect gives you electronic levels that are very, very energetically deep. So if you look at the conduction and valence band edges of the diamond, your ground state for the NV center is about halfway between your 2 bands. And that gives you enough headroom that you can even have orbital excited states that are also very far away from the band edges. So to first order, this really does look like molecular orbitals, where you don't really need to consider the lattice when you think about the electronic degrees of freedom for the NV center. So it really looks like, you know, a trapped molecule inside this diamond lattice. The NV center has a ground state electronic spin. It's a spin 1 system with very, very long coherence time. So at room temperature, the spin lattice relaxation time is about 10 milliseconds. And then the T2, the spin coherence time, is basically just limited by how isotopically pure you can make the surrounding diamond. And it turns out that there's this very convenient way to optically manipulate and measure the spin, even using very unsophisticated lasers. So you have off-resonant excitation, where I basically take something that's the equivalent of a green laser pointer, and if I shine that on an NV center, it turns out that if I start in one spin sublevel, you know, I get some number of photons per second. But if I start in another spin sublevel, I have a spin-dependent intersystem crossing that shelves the population into a dark state. So it just decreases the total fluorescence. So I can use this for reading out the spin, even at room temperature. This is called optically detected magnetic resonance. So here's a plot of, you know, looking at the magnetic resonance at around 2.8 gigahertz just by looking at the total fluorescence. And you can use this, for example, to read out the local magnetic field, because you can look at the Zeeman splitting between these transitions. And there have been a number of, you know, demonstrations of just sort of basic quantum information processing using NV centers, where you can look at coherent oscillations between these spins and use it for a variety of tasks. So because of this set of properties, there are now dozens of groups around the world that are all looking at the NV center in Diamond for quantum information processing and quantum sensing. For the specific application of quantum networks, there are actually only 2 properties that we really care about. So this off-resonant readout is, you know, a very convenient thing and is a nice tool, but it's not really critical to quantum networks. What we care about are, you know, first, you of course need these very long electronic spin coherence times. But second, in order to do the spin photon entanglement, you need narrow spin conserving optical transitions. So if you get to sufficiently low temperatures for the NV center, this is around 10 Kelvin, then you have these nice optical transitions that are really connected to particular spin sublevels, and then you can use that as the basis for spin photon entanglement. Based on these properties, there's been this really beautiful march of experiments on deploying NV centers in you know, demonstrations of quantum networks and remote entanglement, mostly in the groups of Misha Lukin at Harvard and Ronald Hansen at Delft. And it's, you know, this really impressive march where they demonstrated spin photon entanglement, 2-photon interference, remote entanglement, quantum teleportation, entanglement distillation. And this sort of culminated in this really nice experiment in Ronald's group a few years ago, where they took 2 NV centers over 1 kilometer apart on the Delft campus, you know, in separate cryostats, and then used the remote entanglement between these NV centers to do the world's first loophole-free Bell's inequality test. The idea is that they're far enough apart that they can't communicate at the speed of light, which is one of the loopholes. So that's some very beautiful science, you know, and I think Ronald is continuing to sort of build up this platform into a larger network with more nodes. But there's a really huge problem or challenge, I should say, in scaling a quantum network based on NV centers and Diamond. So the entanglement generation rate in that Bell's inequality test that I mentioned was really low. It was something like 1 per minute. They have recently been able to change their entanglement scheme and sort of squeeze out a number of technical improvements to improve this by, I guess it's a couple, almost 2 orders of magnitude, to 39 entanglement events per second. But this is still an incredibly low bandwidth, and this is at very short distances. And the reason that NV centers are really difficult all have to do with their optical properties. So you have these narrow spin conserving optical transitions here at 637 nanometers, but if you just take a photoluminescence spectrum the NV, you can see that there's also all this stuff out here, which is incoherent. And this is emission of a photon and a photon. So this is a big phonon sideband. And this is essentially just loss from the perspective of these schemes. And this comprises something like 98% of the emission. So you sort of enter the problem with an overhead of about a factor of 50. So you have this effective low quantum efficiency in the zero phonon line. The second problem that's actually maybe much more serious is that for the NV center, you have an extremely large static dipole moment in the excited state. It's something like 4 gigahertz per megavolt per meter. And then to give you some physical intuition, what this corresponds to is if I take a single electron about 100 nanometers away from the NV center, and then I pull it off to infinity, that gives me a half gigahertz shift on the optical transition. And you should compare that to the line width of the natural line width of the NV center, which is around 10 megahertz. So even if I can purify the lattice down to part per billion levels of fluctuating charges, you're going to see shifts that are, orders of magnitude larger than the natural line width. So this is a real killer. And remember that for these remote entanglement schemes, I really need these photons to be, very well behaved and on resonance with each other all the time. So there's now a fairly large number of people who have tried to tackle this problem, but it's a very hard material science problem. And this is, maybe my little tombstone of the graveyard of this problem from when I was a postdoc in Misha's group, where we worked very, very hard to make optically stable implanted NV centers where they were pretty close to, the top surface of the diamond. But then as soon as we started sort of nanostructuring and doing nanofabrication to the diamond, because those are relatively uncontrolled surfaces, you can see that you get wild spectral diffusion to the tune of several gigahertz. So this is a real challenge in building anything up on NV centers. So this has motivated a search for alternative defects, and recently there has been a lot of work on the silicon vacancy center in diamond. So the silicon vacancy is stoichiometrically very similar to the NV center. So you take out 2 carbon atoms and you put in a single silicon atom. But the difference in terms of geometric configuration is that the silicon atom is a little bit too large to comfortably sit inside one of these substitutional sites. So it instead relaxes to this interstitial position. So you have a split vacancy interstitial configuration. And this has very different point group symmetry from the NV center. And in particular, it has inversion symmetry. It's in a non-polar point group. And that means that it's sort of guaranteed by symmetry to not have a permanent dipole moment. So because of that, it is less sensitive to electrostatic fields. And you can see that you have a very small inhomogeneous line width. So here are individual silicon vacancy centers, and you detune your laser by just a gigahertz and almost nothing lights up. And by comparison, for the NV center, this would be more like 100 gigahertz to a terahertz in terms of the inhomogeneous distribution. And it's easy to find transform limited line widths and different centers that are on resonance with each other. So these are really much nicer optical properties than the NV center. However, the silicon vacancy center also has very, very short spin coherence times. So even down at 4 Kelvin, the spin coherence time, the T2, is around 40 nanoseconds. And by comparison, the NV center is essentially infinity at 4 Kelvin. It's, I think the longest people have measured is minutes to hours. Sort of depends on your environment. So based on these very nice optical properties, there's again been a very nice march of experiments, mostly in the groups of Misha Lukin, or in the group of Misha Lukin in collaboration with Fedor Yelecko at Ulm and Marco Loncar, who's also at Harvard. And they've done a lot of very beautiful demonstrations of, for example, quantum memory assisted communication by integrating these silicon vacancy centers into nanophotonic cavities where you can have very, very high atom photon cooperativity. However, this spin coherence time, you can sort of freeze out this process at very, very low temperatures, like in a dilution refrigerator, but even down at, the 50 millikelvin that they're operating, the longest T2 that they can get is around a millisecond. So this is going to be a real limitation in getting to long distances or multiple nodes. Okay, so we have two color centers that people have studied intensely. One of them has very nice spin coherence time and kind of lousy optical properties, or I should say extreme sensitivity to its environment. And then the other color center has very, very good optical properties, but then really lousy spin properties. So obviously what you want to do is find another color center that's in the other quadrant where you have both good optical properties and good spin properties. And we have a lot of reason to believe that there are other color centers out there. It turns out that the gemology and geology communities have been just characterizing diamonds and looking for various optical transitions for almost a century now. And this is a handbook that Alex Zaitsev put together almost 2 decades ago now on various optical properties in diamond. And you can see that if you just look in the table of contents, this optical bands section is something like 230 pages long. So there's really a lot that people have characterized. But by and large, a lot of this is just sort of taking a random diamond and seeing what's in there. So for example, the H7 center at 416.8 nanometers, where the H stands for heated, is observed in type 1 diamonds after irradiation annealing at temperatures above 500 degrees. So they sort of know phenomenologically, I can get this center if I get this particular type of diamond, and I can do standard material science heating and beating to try to see if I can move these things around. But in general, they don't know, what heteroatoms are involved, what the structure is, and certainly do not have a full catalog of the quantum coherence properties of any of these defects. So there's a big, frontier out there of trying to characterize even just the centers that we already sort of know about. Just to sort of drive this point home, almost all of the initial work for about half a decade in the excited state of the excited state fine structure of the Envy Center was done with a single diamond that somebody pulled out of a mine in the Ural Mountains. Realized that it had very nice, Envy properties, and then they cut it up and sent it to various groups around the world. So this was the little piece of the magic Russian diamond that I worked with as a postdoc. This is obviously a terrible basis for a scalable quantum network, but also kind of a bad basis for just doing any sort of materials discovery, because you have to sit around and wait for somebody to find a new magic diamond to look at the color center that you want. So fortunately, we have a different approach that's available to us now technologically. So there is now extremely high purity bulk chemical vapor deposition grown single crystal diamond that is just commercially available. And it's really incredible what they've been able to do here. They can sort of routinely grow very large diamonds that have below 0.5 part per billion background impurity concentrations of the most common heteroatoms. There are not that many materials in the world where we're able to do this. It's silicon, because obviously silicon is very important. Germanium, because there's some period of time where we hadn't picked silicon yet. And then just a couple of other materials that have been purified for things like, neutrino detectors and things like that. So this is really a remarkable achievement. And we have now these bulk substrates that essentially act as a background vacuum, where we don't have to worry too much about what's already in the diamond, and we can introduce new heteroatoms to see what kinds of color centers we can make intentionally and systematically. The dumb approach is to just implant the entire periodic table into a diamond, and we are definitely also doing that. But before we go into the very broad search, we can at least take the two color centers that have been very well characterized and see if we can learn any design principles from the properties of those two color centers. So the first comparison is one that I already alluded to earlier, which is that if you look at the point group symmetry of the Envy Center compared to the Silicon Vacancy Center, the Silicon Vacancy Center has inversion symmetry, which guarantees that it has 0 permanent dipole moment. And that symmetry is really what gives rise to the better optical properties in Silicon Vacancy Centers. So that seems like something that we want to try to preserve. Then if we look at the comparative electronic configurations, they actually have very similar electronic configurations. Both NV and Silicon Vacancy have doubly degenerate orbitals in their ground state. But the difference is that the NV center has 2 electrons here, while the silicon vacancy center has 3. So you have this spin 1/2 system with a doubly degenerate electronic orbital. And these kinds of imbalanced configurations are susceptible to spontaneous symmetry breaking, where if you get a little distortion, a geometric distortion, then that breaks the degeneracy. And then because you have 2 electrons down here and 1 electron up here, this is slightly energetically favorable. In silicon vacancy and diamond, it turns out that the energy scales involved here are small enough that what you really have is a dynamic process where this distortion sort of moves around. So it turns out that this very short spin coherence time is actually, it just arises from a phonon-mediated orbital relaxation. So it's an orbital relaxation process that leads to this dephasing. So one kind of naive idea is if I just got rid of one of these electrons, then I would recover a balanced electronic configuration similar to the NV center, while preserving all of the nice optical properties that you have of the silicon vacancy center by virtue of its point group symmetry. So the approach here is to try to use compensation doping to stabilize a new charge state of the silicon vacancy center, thereby accessing this new spin configuration, which should be immune to this phonon-mediated orbital relaxation process. And a few years before our work, there had been some theoretical calculations of this defect. So J. Romays and Adam Ghali had this very nice DFT paper from 2013, where they indeed calculated that the neutral silicon vacancy should have orbitals that are inside the band gap of diamond. It should have a ground state spin of 1. And then they even went a step farther and calculated formation energies for each of these different charge states of silicon vacancy as a function of Fermi level in the diamond. So as you get to more N-type doping, you stabilize more negative charge states, and more P-type doping, you stabilize more positive charge states. And you can see that there's this little island of stability here where the neutral charge state is the most thermodynamically stable charge state. Boron doping takes you to around 0.4 eV away from the band edge, so it should take you right to the edge of this triangle. So in collaboration with Element 6 and De Beers, we worked on developing a modulation dope sample where we could access many different Fermi levels inside a diamond and look at what happened to silicon-containing defects in that diamond. So what you're looking at here is a sample where they grew it with many different co-concentrations of nitrogen and boron, and then grew it thick enough that we could cut it in cross-section and then sort of image each of these layers separately. And this is a UV-PL image of one of these diamonds. This trapezoid is this cross-section. And then you can see sort of different degrees of photoluminescence. This is actually phosphorescence from boron as you look through this diamond. So in this somewhat complicated sample, we were immediately able to see neutral silicon vacancy centers. So in bulk electron spin resonance measurements, you can see this central set of lines that are associated with substitutional nitrogen, which they call P1 centers in this community. But then there are also these satellite lines that evolve around the P1 centers that correspond to a defect that is spin 1 with a zero field splitting of almost 1 gigahertz. And this had been previously characterized by a few groups and labeled as the KUL1 center. KUL stands for Catholic University of Leuven. So it's one of these centers that they had, cataloged in looking through many diamonds. And there was a lot of early work done, especially by Mark Newton's group at the University of Warwick and looking at KUL1. We know that it's silicon containing because you can see hyperfine lines that are associated with silicon 29. And we also know that it's an inversion symmetric center because you just have a single set of satellite carbon-13 hyperfine peaks. Mark Newton's group had also pointed out that there was a correlation between the presence of KUL1 and photoluminescence at 946 nanometers, and we were able to also see that in bulk photoluminescence. However, in these complicated samples, there are quite a few other lines and other photoluminescence in general, and not all of these have been cataloged previously. So it's actually unclear, how to definitively associate lines that you see in PL with lines that you see in spin resonance. And in particular, if I gave you a sample that had 10 spin resonance lines and 10 optical lines, and asked you to find, all of the covariances so that we could just make a bunch of samples and figure out what correlates with what, you have something like 3 million possible combinations. So this is actually really hard to do with this kind of traditional material science approach of just developing more samples and looking for correlations. So we set out to try to figure out a way to do these assignments more definitively, and we did something quite simplistic. So we just took a multi-mode fiber, put it down into the bulk ESR rig, and then shined resonant light on the sample. So we basically had a tunable laser, and the hypothesis was that at sufficiently low temperatures, no optical transitions are infinitely cycling. So I should be able to do something to the spin polarization, whether it's a lot of spin polarization or a lot of depolarization, I should see some feature. And indeed, what you see is as we scan over 946 nanometers, we get these very narrow features in the bulk spin polarization that are really dramatic. So we get up to, tens of % of optical spin polarization. And we even found kind of an extra set of optical excited states that we could now definitively associate with SIV0. Okay, so armed with this assignment, where we know that the 946 nanometer emission also comes from the KUL1 line, we can go back into this really complicated sample and do PL mapping to figure out where we see a lot of 946 nanometer emission. And then do a lot of other spectroscopy to figure out what's going on in these bands. So you can see that it's really localized to just a few bands, and use that to develop a recipe for now trying to intentionally stabilize SIV0. So this is now a uniformly boron doped sample where we implant with silicon and we achieve 80% conversion efficiency into SIV0, which shows that we can really create substrates where SIV0 is the thermodynamically stable charge state. And now in this high purity, well-controlled sample, we're able to see very long electronic spin coherence times. So the spin lattice relaxation time is around a minute below 20 Kelvin. And the T2 time is around a millisecond, but this is just limited by the natural abundance of carbon-13 in the environment. So we can dynamically decouple that slowly varying path away to get to coherence times of almost a second. So we have very long spin coherence times. And again, what you should compare this to is that the spin coherence for SIV minus at these temperatures is in the tens of nanoseconds. So now we can also characterize the optical properties of silicon vacancy neutral. So this is now a lower density sample where we're able to isolate single centers in confocal microscopy. We know that they're single centers because we can do photon correlation statistics. And now when we look at PL from these single centers, instead of this sort of broad inhomogeneous line width, we really see something that's spectrometer limited. And we can do a very careful job of sort of calibrating our spectrometer to look at the spectrum. And what we find is that really all of the emission is in this very narrow zero phonon line at 946 nanometers, and out to about 1,000 nanometers, we see very little emission in a photon sideband. There is a tiny bit out there, but we can kind of put a lower bound on the Debye-Waller factor of 90%. And what you should, again, compare this to is the NV center, which has only 3% of the emission in the zero phonon line. And then finally, in order to actually characterize these line widths in more detail, we do photoluminescence excitation spectroscopy, where we collect the very, very little emission that you do get in the photon sideband. So these are somewhat painful measurements, and scan a narrowband laser across this absorption line. And what we see is that we have a line width of something like 100 megahertz that's completely stable in time. And what you should compare this to is the natural line width given by the excited state lifetime, which would be 80 megahertz. So even in this, sort of ion implanted sample that's heavily damaged, we're able to get essentially transform limited line widths for individual silicon vacancy centers. And just to show you that we're not cherry picking the data, we can then do, ensemble PLE and look at this heavily implanted sample. And we really find that every single center we look at has optical transitions that are just a couple hundred megahertz. Okay, so far I've shown you that we can make the neutral silicon vacancy center It has very long spin coherence times and very coherent optical transitions and high quantum efficiency into the zero photon line. And now what I want to do is try to find a way to connect the optical transitions with the spin. So one first step to that is to figure out how to do optically detected magnetic resonance. So now I have a little bit of a side story that I promise will get us back to ODMR in 2 slides. But basically, so there was a postdoc and a student who were working on spectroscopy of silicon vacancy neutral, and they noticed in a couple of these samples that we could see a whole forest of transitions in absorption between 800 and 900 nanometers. And they said, hey, this might be interesting. And I actually told them, ignore that because we have no reason to believe that these are silicon vacancy related at all, because these are complicated samples. But then, I had pretty good reason to tell them to ignore it. So if you just write down all of the allowed electronic orbital states by group theory, we basically predict that there should be 3 excited states. And we found 2 of them, right? So we have 946, and then I alluded to earlier that there's this 951 transition. And there was some very nice work by Ben Green and Mark Newton a couple of years later, where they sort of definitively showed the properties of this 951 transition. So we're only missing 1 other higher lying excited state. So it seems sort of implausible that you would see, dozens of transitions basically associated with the center. And also there was some prior art where people had looked at synthetic diamonds all the way back in the 90s, and they could see a number of absorption lines down in this range that were unassigned, and they could also see them in photoconductance. Fortunately, the student and postdoc just ignored me and instead went and did some more detailed spectroscopy. And what they discovered is that if you pumped at one of these lines, so you take a laser, tune it to 830 nanometers, and then you look at emission at 946 nanometers, you could see basically all of the same lines. So this is photoluminescence excitation, where you're looking for photoluminescence at 946 nanometers. So the fact that you could see emission at 946 associated with these transitions really shows that these are somehow associated with silicon vacancy neutral. They could also play the same trick that I talked about earlier, where you look at optical spin polarization by shining in light and then looking at the total spin polarization in bulk ESR, and they found kind of the same forest of lines with a slightly different shape, but basically the same multiplicity. And they also found kind of an extra set of lines down here at 885, 890. Okay, so this is all quite surprising that there are so many higher lying transitions, and it took us a little while to sort of puzzle out what was going on. But what we knew is that technologically, this was very interesting because you could get very, very efficient optical spin polarization. So pumping on some of these lines, you could get bulk spin polarization in excess of 60, 70%. So this is sort of a nice convenient tool for being able to optically initialize the spin. So the model that we ended up developing in collaboration with Adam Gali, who is a DFT theorist in Budapest, was that these higher lying transitions are associated with Rydberg-like bound exciton states. So the idea is that you can think about your silicon vacancy neutral as a silicon vacancy minus center with a very loosely bound hole. And then this hole should have hydrogen-like states, 1s, 2s, 2p, 3p sort of states that inherit some of the properties of the some of the properties of the band structure with some, perturbation from the silicon vacancy center. Adam's calculations show rough agreement with the sort of splittings and positions of these states. And what we find is that, we're probably looking at the 1s, 2p, 2s, and 3p transitions. And then you very quickly run into sort of the ionization continuum close to the valence band edge. So now, armed with this sort of new manifold of states for being able to do very efficient optical spin polarization, we're now able to do optically detected magnetic resonance. So we can polarize at 855 nanometers. Sorry, this is from some old slide deck. Obviously, there are no posters at the summit. We can polarize at 855 nanometers and detect at 946 and scan a microwave tone. And what we find are again, this magnetic transition around 940 megahertz. And then these are satellites associated with silicon-29 because this is a silicon-29 enriched sample. And then we can use this to look at dynamics of the spin, or we can do T1 and T2 measurements. Okay, so to just briefly summarize, we stabilized the neutral charge state of the Silicon Vacancy Center in Diamond, which is an excellent candidate as a single atom quantum memory for quantum networks because it has a very long spin coherence time and also has excellent optical properties where we see very narrow, stable optical transitions with near transform limited line widths and high quantum efficiency in the coherent part of the emission. We've used this sort of surprising higher lying manifold of states to observe optically detected magnetic resonance for the first time. And now what we're currently working on is some fine structure spectroscopy to try to establish a good entanglement, spin photon entanglement scheme. And we also continue to work on sort of optimization of synthesis of boron doped diamond together with element 6. So there are a couple of directions in addition to that near-term goal that we've been working on as well. The first is that this wavelength range now gives us access to kind of new types of integrated devices. So in particular, we're in the transparency window of gallium arsenide. So you can imagine heterogeneously integrating gallium arsenide with diamond to make integrated photonic devices. I'll talk about that a little bit more, time permitting. But second, I'll just mention that everything that I told you about programmatically is very generic in that we just used ion implantation to discover a new defect, and then did a lot of bulk spectroscopy to show that it was an interesting defect to pursue. So we're now sort of deploying this general playbook to do a much broader systematic search for quantum defects in diamond and also in other host materials. And in particular, in collaboration with Jeff Thompson, Steve Lyon, and Bob Kava, we're currently working on looking for new host materials for rare earth ions. Rare earth ions are very promising quantum systems, particularly for telecom wavelength quantum networks, because you can use erbium, which has which defines the telecom standard in some sense. You have a 1.5 micron emission band. However, all of the currently known host materials for rare earth ions have stoichiometric nuclear spins. So what we're working on is taking nuclear spin-free substrates of reasonably high purity, and then doing ion implantation and thermal processing, and then using bulk spin and optical characterization for rapid feedback. And then basically, once we find sort of a good defect host combination, then we can do the single atom characterization. And we have a number of recent results along those lines where we have some very promising new host materials for erbium. I'll just mention briefly a couple of things about our efforts to try to integrate these neutral silicon vacancy centers into photonic devices. So what we're currently pursuing is heterogeneously integrated devices constructed out of 3,5 materials that we then transfer onto the diamond surface. The idea is that we worked very hard to get diamonds that have the properties that we want. So it would be better if we didn't have to continue to do nanofabrication on the diamond itself, but instead could get a lot of functionality out of something that has already been proven to be a good photonic material. The challenge here is that diamond has a very high refractive index. So you basically lose a lot of light directly into the diamond. So we've worked a lot on heterogeneously integrated photonic crystal design. It does turn out that you can get, for reasonable parameters, a pretty nice band gap on diamond, an optical band gap, or I should say photonic band gap. And we can do this parameter optimization. And we find that for sort of reasonable fabricatable parameters, we can get up to quality factors of 10 to the 5 to 10 to the 6, which is state of the art in gallium arsenide. The other kind of small drawback is that, of course, your color center is now sitting in diamond and not at the field maximum of your photonic device. So you take a small hit from being in this evanescent tail. But it turns out that for this design, that hit is only something like a factor of 4. So that's reasonable for these kinds of devices. The other kind of opportunity that's really interesting once you go into a new material is that we can think about more complicated integrated devices like doing on-chip quantum frequency conversion. So the scheme that we've been pursuing so far is four-wave mixing Bragg scattering. The idea is that we have two pumps that we turn on, one at the telecom band, one at the telecom band, one that's close to 946. And then you put in your signal photon from your silicon vacancy neutral center, and out you spit a single telecom photon. The nice thing about nanophotonics is you have a lot of freedom to kind of tailor the dispersion of your structure just by sort of changing the dimension. So the game here is that, okay, you can draw this diagram that conserves energy, but then you also need to find some way to conserve momentum. And the way that you can achieve that is by basically matching the group index at these two different wavelengths. So here we can pick kind of a dimension of this waveguide that matches momentum from 946 and 1550. And what that should do is sort of enhance this four-wave mixing Bragg scattering process and sort of suppress other processes that are not momentum matched. So we've made some first strides towards doing these integrated photonic crystals. We basically just do gallium arsenide fabrication as you would normally and make these suspended structures. And then we sort of took a page from the 2D material playbook and made these polymer stamps to pick up gallium arsenide and transfer them onto the diamond. And then you sort of lift that off and clean off all of your polymer, and you end up with this gallium arsenide on diamond structure. And we've been able to get sort of reasonable quality factors in this first pass. Okay, so let me take a moment to thank the people who worked on everything that I talked about today. The silicon vacancy neutral work was led by Brendan Rose, who was a postdoc in my group, and Ding Fog, who is my first graduate student, who actually just defended his thesis and is leaving. I think his last day in my group is tomorrow. And then a lot of the other work on detailed spectroscopy of silicon vacancy neutral was led by Zhiwei Zhang, who is a graduate student in my group, and Paul Stevenson, who was a postdoc who recently left to start his own group at Northeastern University. The heterogeneous photonics project that I discussed very briefly is led by Ding and Alex Abulnaga, another graduate student in my group. I should also mention that we did a lot of the ESR work in collaboration with Steve Lyon. On the photonics project, we worked heavily with Jeff Thompson's group. And then we have a number of collaborators, both on the diamond growth side, Matthew Markham, Nikki Palmer, Andy Edmonds, Dan Twitchen at Element 6, and Brad Kahn at De Beers. And the diamond characterization side, Lee Wang and his team at the Gemological Institute of America, and then Adam Ghali and his student Gergo on the theoretical calculations of SIV0. And I have a number of funding agencies to thank, but let me just put in a very small plug, since I think this is a broad audience for the quantum community at Princeton. So we launched the Princeton Quantum Initiative in 2019, and this is a really exciting, broad community. I think this is actually an outdated face page now. But there are a number of people working on various aspects of quantum computing and quantum information processing, quantum networks, and different types of physical platforms. And we also have a PQI postdoctoral fellowship, and the applications are due December 1st if anyone is interested in applying. And this PQI all plugs into our NQIS Center, which we are leading together with Brookhaven National Lab, Yale, MIT, IBM, and many, many other partners, the Co-Design Center for Quantum Advantage. And I'd be happy to take your questions. Thanks.
Hey, Nathalie, thank you. Thank you very much for that very, very interesting talk. You know, like these days, people have these conversations that quantum 2.0, right? Next quantum systems is all about finding different opinions from different scientists that go beyond just physicists in order to improve the systems, right? And I think what you just showed us today here is exactly a wonderful example of how do you take a system that the physicists like, and then you take thinking from chemistry people and material scientists make it better, improve it, and getting closer and closer to the thresholds where then you can start building very interesting things. I think this is really wonderful. All right, so then remember now the talk is open for questions, right? If you are not shy, you can ask the questions yourself just by unmuting yourself, or if you want to type questions in the chat, then we can read them. We can read them for Nathalie. All right. But maybe perhaps let me open with some questions, and then as the rest of the audience start asking questions. So one of the things that you say there at the beginning, Nathalie, is that the generation rates of the NV-Diamond centers, for example, in the experiment that are doing in Delft, is limited, right? And then once you go into like longer distances, this becomes very, very small, right? And then you have to have integration times of days or weeks, perhaps even months, right? With these new systems that you have you quantified what is the advantage in terms of these sort of quantum information rates that now you're getting in the may I call them the Catholic systems?
Yeah, so it's a very good question, and it's probably one that I should have a sharper answer to. But the truth is that the devil is really in the details. So in particular, we have not demonstrated a spin photon entanglement scheme. And I think any kind of final entanglement generation rate is going to depend very, very heavily on the cyclicity of the particular transition you're using, and sort of how easy it is to separate right, like you're going to have very different results if you're trying to do polarization based spin photon entanglement versus time bin spin photon entanglement. And a lot of, for example, this distance from 1 per minute to 39 per second was coming up with a new entanglement generation scheme. And that's an enormous factor. So I guess what I will say is that if you just kept that constant, if you assume that we have the same kind of readout that you can get with NV centers, the real advantage here is that you should be able to integrate these centers into photonic devices and then achieve extremely high cooperativities. So Misha's group with silicon vacancy minus has achieved, as far as I know, the world record in terms of cooperativity in any system. So if you could sort of take advantage of that, then that should allow you to gain a couple of orders of magnitude, a few orders of magnitude. We also have a faster excited state lifetime than the NV, although that could kill you in other ways. And then the other kind of big boost is going to be in this quantum frequency conversion, because if you just use direct 637 nanometer emission, then obviously you're not going to get very far. You can get to a few kilometers before you've lost all of your light. So what the final number will be will also depend on how efficiently you can do that quantum frequency conversion and what your noise sources look like.
All right. So any questions from the audience?
Hi, Nathalie. I had a question. Could we use this diamond device like a qubits?
Yeah, you mean like for quantum computing or quantum simulation, as opposed to qubits for quantum. I mean, it is a qubit. So it's but in a sense, you could think of a quantum repeater as being a very tiny quantum computer at each of your nodes where you're performing quantum error correction. Yeah, so there are a number of people who are trying to do quantum computing and quantum simulation with NV centers in Diamond. The problem with almost all of these solid state defect-based systems for quantum computing is that it's hard to scale 2 qubit gates. So if you rely on, for example, dipole-dipole interactions between your spins, then now, and phosphorus donors and silicon have the same problem. Now you have to have very precise placement of your arrays to be able to, actually do all of your 2 qubit gates. And building up chains is really hard. So it's sort of an outstanding problem. There's maybe a slightly more promising approach, and there's a very nice paper that was recently posted on an archive by Tim Taminiaz along these lines, where you can basically make like a local register out of your NV center and surrounding sort of nuclear spins, and then use that for modular quantum computing, where you then use spin photon entanglement to kind of connect multiple NV centers. So there are definitely people who are thinking along these lines, but I would say that it's still a very sort of high risk path.
Okay, thank you.
All right. Do we have more questions from the audience? So here's another question there, Nathalie, following up on what you say. Maybe perhaps a couple of questions. This is all very interesting stuff. Now that you have these new systems, right? And you say that one of the most important things is to do the internal gate with some form of a long-lived excitation inside the crystal, right? Akin to what they do there in Delft. How would you envision doing this in this new system? Would you have to add some doping? What are the steps that you have to follow to do that?
You mean just like what's standing in our way from just building a quantum network already?
Yeah, right. I guess that
yeah.
Mm-hmm.
No, so I mean, so the very first piece is the one that I keep on bringing up, which is just a scheme for spin photon entanglement. So we're currently working on sort of excited state fine structure spectroscopy, which is sort of a boring answer. But right, what we need to establish are sort of the detailed selection rules for you prepare the spin here, it ends up in this excited state, where does it go, and
So I
taking out
think
all the
it's a
different,
transcript.
the different branching ratios. So that's the first piece. From a practical standpoint, actually, I would say that one of the big challenges along these lines has been that there are no real sources of very high purity boron dope diamond. So De Beers can do it. De Beers and Element 6 can do it. They did it on a single reactor, and we've actually been trying to reproduce it on other reactors with not very much success. So we currently have, a batch of diamonds where the properties that we see are very reproducible, but then we look at other diamonds that we think should look very similar, and then we get very low conversion efficiency to silicon vacancy neutral. So there is still a materials question, how you optimize these things and what the good proxies are to look at. And then I think, again, this quantum frequency conversion is a very important problem to solve. And there are other folks that have made very nice strides along these lines. The 4-wave mixing Bragg scattering scheme that we're pursuing is completely copying from Kartik Srinivasan's group, where they were able to show very high conversion efficiency from gallium arsenide quantum dots, so at 980 nanometers out to 1550. So our hope is that it should be relatively easy to pursue in the system, because it's very close in the wavelength range.
All right, so here's a question that relates a little bit to what you say, using the vacancy systems for computing, right? So Alan asked, this is a little bit more of a general quantum computing question, but he's asking that because of the cost and complexity of production, do you envision quantum computers integrated to classical computers, in which the quantum computer is a little bit more like an add-on, a quantum processing unit? And do you think that's a viable scenario in which quantum computers are like an add-on silicon, like a solid state system like yours, that then you put together into your interprocessor, and then you have kind of like a hybrid? Is that an idea?
Yeah, so I think nobody envisions a world where we replace all of our computing tasks with quantum computers right now. So there are a very small number of tasks where people have really proven that a quantum computer can do better than a classical computer. And then, of course, there's a very broad class of problems that sort of generically fall under the rubric of quantum simulation, where, of course, a quantum computer can be better at simulating some Hamiltonian than than an arbitrary classical computer. So we're always going to be living in some kind of hybrid world, even if quantum computers are wildly successful beyond all of our crazy dreams. I guess maybe what I would sort of emphasize is two things. One is that I think there are always going to be really interesting problems on the classical layer, because you still have to do things like control and figuring out how to compute what gates to apply. And I think, we're only now, okay, this is very far away from diamond stuff, so I won't talk too long about this, but I say that we're only now as a community getting to a stage where people are building complex enough systems where it makes sense to think about these things. But there are a number of people who are thinking about, like what you do at higher layers of the stack. How do you optimize the execution of particular algorithms? And a lot of that is, is very classical. It's informed by the underlying quantum hardware, but I think there's a lot of sort of new optimization problems and ways to think about code design, for example, all along the stack. But the second thing that I'll say is, for quantum computing, building the first logical qubit is kind of the big, like the first fault tolerant logical qubit is the grand challenge, right? So you can sort of do whatever you want in terms of building a system with 100 physical qubits or 200 physical qubits or whatever. But so far, nobody has really articulated a real path towards the first fault tolerant logical quantum qubit, quantum bit. So I think what that means, if I were being maximally optimistic as opposed to cynical, is that there is a broad range of opportunities for new physical systems to get us there. And some of those things could look very surprising. To give you one example, this beautiful cat code stuff that is happening at Yale, I think people would have found extremely surprising just 10 years ago, right? And nobody was thinking along these lines of like, let's just build a bosonic code computer. And once you've sort of opened up that whole frontier, then it opens up like a whole bunch of new possibilities that people hadn't previously considered.
Fantastic. Do we have more questions from the audience? Well, if that's not the case, I will ask you a question that I asked also our previous speaker, right? A lot of the audience that we have in this summit is people that are trying to get immersed in quantum information and see, can you get into a nice PhD or a master's degree or a postdoc? Could you please tell us from your perspective, if you were a grad student, what topic would you choose? Maybe 3 or 4 topics where you would like to then redo your PhD thesis, for example.
Yeah, that's very interesting. I don't know, if I really redid my PhD, I might go work on like magnetic navigation on birds or something completely different. But no, so I think what I've been noticing about the younger generation that's very different from when I was in grad school or even when I was in my postdoc is that there are a number of people who are much more fluent across the physics quantum information boundary. And I think part of it is driven by the fact that, again, we can finally build complicated enough systems that it makes sense to really work at that interface. Right, like 15 years ago, it was all just like, I need to design a new qubit and do single qubit gates. And you just don't need to know very much quantum information to work on single qubit gates. Or in atomic systems, it was, you have to do a lot of atomic physics, right? So I think there is a really exciting frontier now where if you have the ability to cross that boundary fluidly, that you can make really big contributions. Conversely, I would say that one of the exciting things about building big systems and trying to build tools that work is that you can really have contributions from many different fields now. I think, for better or worse, this field has been completely dominated by physics for the last couple of decades. But I think it's fairly clear that now, you know, entrants from other disciplines can make a pretty big contribution.
Wonderful, Nathalie. All right, this is a last call for questions from the audience. Well, and it seems like we don't have more questions, but there's going to be a second opportunity tomorrow, right? Tomorrow we're going to have a panel discussion in all things quantum network and quantum internet, and Nathalie has very kind to also be there tomorrow, so we have opportunity for more questions. And then, well, for now, we thank you very kindly, Nathalie, for this wonderful talk, right? And again, once things are getting a little bit better, we look forward to invite you here so you can see all the activities that we have, so you can talk to all the profs here, all these wonderful interdisciplinary research that you're doing. And then we'll see everybody tomorrow morning, right? Thank you very much and have a nice rest of the day.
Thank you so much.